Hello, this is Gary LaRue, Technical Editor at Microwave Journal. I'd like to welcome you to today's webinar, an informative tutorial discussing high-frequency materials for 5G base stations, presented by John Hendricks and John Coonrod of Rogers Corporation. Before we begin their presentation, let me cover a few items about navigating the webinar. In the center of your screen, you'll see a window containing the presentation, which you may enlarge to full screen to have a better view of the slides. The window labeled Resource List, which you can access from the green box at the bottom of your screen, contains a copy of the presentation, which you may download at any time. The webinar is being recorded and will be available for replay about an hour after we finish, allowing you to watch it again and recommending it to colleagues who weren't able to join this live event. You'll find a link to the recording in the Events section of the Microwave Journal website. After the presentation, we will have time for the presenters to answer questions, so if you'd like to ask one, just type it in the Q&A box on your screen at any time during the hour. If you have any technical problems, you may submit a question in the Q&A box and we'll try to help you, or you can click on the yellow box with a question mark at the bottom of your screen, which will take you to a user's guide. That's it for the instructions. Now let me introduce our speakers. John Hendricks has been with Rogers for almost 30 years. He currently works as a market segment manager for the Advanced Connectivity Solutions segment. After graduating from Manchester University in England with a bachelor's in physics, he joined Marconi Defense Systems, where he worked as a microwave engineer, before moving to the test and measurement world at Rohde & Schwarz. John Coonrod is the technical marketing manager for the Advanced Connectivity Solutions segment at Rogers. He has some 30 years experience in the printed circuit board industry, split between circuit design, applications, processing, and materials engineering of flexible printed circuit boards, and electrical characterization and application support of high-frequency circuit materials. John is the chair of the IPC D24C High-Frequency Test Methods Task Group. He received a bachelor's degree in electrical engineering from Arizona State University. John Hendricks, I'll turn the screen over to you now to begin the presentation.
Thank you very much, Gary. Okay, good morning, good afternoon, everybody, wherever you are. First, just a very brief overview of the agenda. I'll start with a market overview for 5G base stations. And then between us, John Coonrod and I will talk about the differences in material requirements for 5G compared to 4G. And John Coonrod will talk about the design and PCB fabrication issues that will affect printed circuit board performance. Okay, so briefly, what is 5G? There's a lot of talk about it. There's a lot of hype about it. Self-evidently, it's the fifth generation of cellular network. One important thing is that it operates mainly in two different bands. There is the so-called sub-6 gigahertz band, which is actually down as low as around 600 megahertz and up as high as 5 gigahertz. And then there is the so-called millimeter wave band, which to start with operates at 28 gigahertz and 39 gigahertz, but there are plans to go higher in frequency later on. The initial deployment of 5G networks is starting in places like South Korea, mainly the sub-6 gigahertz band. There is some deployment initially in the USA, which starts out with millimeter wave deployment, but also is beginning to show some sub-6 gigahertz activity. And initially in China, there is a large-scale implementation about to be rolled out really right now as we speak, and that's entirely in the sub-6 gigahertz range. So what are the advantages of 5G? Very briefly, not surprisingly, it runs at much higher speeds, hundreds of megabits per second. Perhaps one would expect that. It also has a much lower latency, so a much faster reaction time, a combination of air latency and server latency in the range of around about 10 milliseconds each. So the system is much faster to react. And one of the things that gives us is a range of applications that moves much further beyond typical mobile applications. Initially, the applications as defined by the International Telecoms Union are what we call enhanced mobile broadband, ultra-reliable low-latency communications, and massive machine-type communications. And there's a couple of slides about that to say a little bit more. So moving on to the next slide, you see almost every discussion about 5G shows a picture that looks a little bit like this. And it's a triangle, and we talk about 5G use cases. And again, we see those enhanced mobile broadband. That's typically mobile phones and fixed wireless access. Massive machine-type communications tends to be enhanced Internet of Things. And then the ultra-reliable low-latency applications are coming later. That's more things like the connected car, for example. And we'll say a little bit about those in more detail. So the enhanced mobile broadband is what's running right now in 5G. So almost everything falls into that first category. That is typically faster data rates for mobile broadband driven by things like the desire to stream or download movies much faster than before. Things like augmented reality and virtual reality. But also in the USA, it's starting as in fixed wireless access. And what that is an alternative to cable or internet for homes and businesses. So that's not a mobile application, that's a fixed application that's different from a typical mobile system in the past, like 3G or 4G. The next application in a little more detail was the massive machine-type communications. That's not the initial application to start with here. That's what you might call Internet of Things, but right now 4G is quite capable of handling any IoT challenges that get thrown at it. IoT doesn't have to be particularly fast, but eventually it will become very, very dense. And so ultimately what 5G would give you is the potential to have far, far more IoT devices. And one of the numbers that gets thrown around is typically 1 million devices per square kilometer or one device per square meter. So 5G gives you the ability to have a vastly denser network of IoT systems going into the future. So the third application would be ultra-reliable and low-latency communications. A few examples of this would be a self-driving car, for example. So ultimately, autonomous driving will rely not just on the independent sensors that cars have, but could also use information that's transmitted through a 5G network. And one of the reasons why 5G would be useful for this is that, for example, these are applications where you can't afford to have a dropped line or a dropped call. So right now, if you're simply making a telephone call to somebody and the line drops out, it's inconvenient, but you really don't want to have connections being dropped if you're using that technology to have an autonomously driven car or a remote control medical surgery or something like that. So 5G has the potential to give you far more reliable connections, which expands the kind of applications that it can be used for. So moving on from a little bit of information about the market, the next question is relevant for printed circuit board materials, and the question here is, what is the difference between 4G and 5G that's relevant for our materials? Well, to start with, there's the frequency side of it. At 4G, those frequencies are typically 700 to 900 and 1800 to 2600 megahertz, where the dielectric properties of the material are the most important. With 5G, you have these two different bands. You have the sub-6 gigahertz, which is broadly similar in frequency to 4G, where the dielectric properties of the materials are very important. But then you also have this millimeter wave band, which is much higher, an order of magnitude higher. And there, the properties of the dielectric are not the only important thing, but the properties of the copper foil are very important, and also the way those printed circuit boards are fabricated, surface treatments and things like that become much more important. So there are extended properties of materials that are important for millimeter wave 5G, but don't necessarily apply to 4G. So that's one difference. Another difference with 4G and 5G are that with the antennas in 4G, you have simple MIMO antenna designs. That means you would have relatively few transceivers and relatively few amplifiers, and those power amplifiers are much higher in power. With 5G, everything is massive MIMO, so you have far greater number of transceivers, and you have a far greater number of power amplifiers, but they tend to be lower power. So you have greater number of power amplifiers, but lower power. Another difference, if you come to the antennas, would be PIM, or passive intermodulation. In 4G, passive intermodulation was a real big deal because these were FDD systems typically, and the antenna and the rest of the systems used to have PIM that typically needs to be lower than 163 dBc, and that has a big impact on the properties of the dielectrics that are required, or the property of the materials, driving the need not just for low loss, but for ultra-smooth copper to reduce passive intermodulation. With 5G, the systems tend to be PVD, and therefore there is much less focus on passive intermodulation, and so that translates into requirements for smooth copper that may not be as strict as they are for 4G, for example. So 4G PIM is important, passive intermodulation is important, 5G passive intermodulation is not so important. And then the final difference on this slide is with 4G, you had fewer active antennas, which meant that typically you had double-sided PCB antennas, or antennas that didn't use PCBs at all. Base station antennas that might be a combination of bent metal and cable were very common. With 5G, it's active antennas, and so you can't really get away with this sort of bent metal and cable approach that you had in the past. So 5G antennas tend to be multi-layer printed circuit board antennas, and because of the active nature of the design, they always require flame retardant materials, whereas in 4G, the materials did not necessarily have to be flame retardant. So that's a brief overview of the differences between 4G and 5G for the material types. So going forward for the next few slides, John Kuhn and I will start by talking about materials for power amplifiers. Then we will move on to materials for antennas, which will be treated separately. And the third area where we will be talking about the higher frequency band, the millimeter wave. So we start with the sub-6 gigahertz power amplifier area. And here we find that there is not necessarily so much difference between 4G and 5G. So for 3G, 4G, 5G, in that typical similar frequency range between 600 megahertz and 6 gigahertz, the current generation of materials broadly meets the needs of both 4G and 5G. There is this greater integration and higher temperature requirements sometimes that drives a need for higher thermal conductivity materials, so we'll talk a bit about higher thermal conductivity. Occasionally at the very lower frequencies, like 600 or 700 megahertz, there is a need for size reduction, so that drives the adoption of higher dielectric constant products because that will reduce the size of the PCB. That's not such an issue when the wavelength is lower at the higher frequency range, but for the lower frequency range, yeah, higher dielectric constants will help reduce the size. And as mentioned, often very important as you move to more multi-layer board and hybrid constructions, lower cost PCB manufacturing becomes quite an issue. We still have some applications where the lowest loss is required, and there we tend to move to PTFE-based materials that offer the lowest dissipation factor. And we will discuss the TC350 and TC350 Plus laminates that offer the best thermal conductivity. So to summarize some of those, the materials of power amplifiers that are currently offered, we tend to break, and there are other materials that are not included here, but this is essentially the range of products that covers most of the needs. We tend to break them down into the base resin system. So you have the PTFE materials at the top in yellow, and the thermoset materials at the bottom in green. And again, depending on the application or the desired properties, at the top you have the lowest loss materials with the lowest dissipation factor. There you have the PTFE materials 3003 and RO3035. If you need a combination of low loss and higher dielectric constants for size reduction, then people start to look at the 3006 because that has the dielectric constant of 6, and that enables size reduction in the PCB. So that's something that people look at for the 600 to 700 megahertz applications. For the highest thermal conductivity, we talk about TC350, but particularly now the new material, the TC350 Plus. The interesting thing there you see is the fourth column where you have the thermal conductivity, which is close to double the thermal conductivity of the existing materials. So for the highest thermal conductivity and thermal management and maintaining lower temperatures at higher powers, we talk about the TC350 Plus. That's a very exciting product. However, at the thermoset end of things, we talk about materials that have been around a little while, and still the most popular material for power amplifiers in 5G, just as it was for 4G and 3G, is the trusty old RO4350B. So that material has been around for quite a while. It is a low-cost material. It has a good range of properties. And as a thermoset, it is compatible with all PCB fabrication requirements. You can make hybrid boards. You can mix it with FR4, and it continues to be a highly successful material. But we do mention two other products, the 4835 laminate. So that material is very similar to 4350B. The only difference is that it does have improved antioxidant performance. So if the material is going to be exposed to higher temperatures for a longer period of time, we would recommend the 4835 because of its improved thermal aging over long-term exposure to higher temperatures. And then finally, if you can tolerate a little bit of higher dissipation factor and you want the benefits of the thermoset RO4000 family, but you want the size reduction that's required at the lower frequencies like 600 megahertz, then we have the 4360G2 laminate system. That's basically RO4000, but with the higher dielectric constant of 6.15, and again, that will enable size reduction at lower frequencies. So that's a brief introduction to the market and the materials of power amplifiers. I'm now going to hand over to John Coonrod, who's going to go into some more detail.
Well, thank you, Mr. Hendricks. And what I decided to do is go ahead and talk about the materials used at sub-6 gigahertz for 5G. And to begin with, I wanted to talk about thermal management, though, because that can be an issue. So I thought I'd go through a few slides to, kind of go through some of the basics of thermal management and then show some of the materials used for power amp at sub-6 gigahertz and some of the reasons why. So to begin with a quick overview of thermal management, as probably most of you are aware, that insertion loss can be a big deal because there's a lot of trade-offs with thermal management. And basically what happens is the more insertion loss you have, the more heat's going to be generated. So that's one side of the coin. The other side of the coin is thermal flow or heat flow and how thermal conductivity plays a role there. I've had a lot of customers before ask me, so how much power can you put into this individual circuit? And my response sometimes surprises them. It's like, well, you can put as much power as you want to in there as long as you don't violate the MOT. And that's the maximum operating temperature of the printed circuit board as rated by UL. So that's really the limit as I see it. And really understanding the variables that impact insertion loss and heat flow is kind of the critical thing for thermal management. So just going through a few slides of some basic thermal management concerns and how that relates to printed circuit boards. What I'm showing here is basically right out of a Physics 101 text, and it's just showing how heat flow works. And the formula there gives you kind of some relationships for the different aspects of heat flow. And really what we're looking at is a simple model where you have a hot reservoir in red, cold reservoir in blue, and they're connected together by some kind of thermal conductor. The interface where that thermal conductor is connected to the hot and cold reservoir, that area is A in the formula. K is the thermal conductivity, L is the distance between them, and T sub H, T sub C is the temperatures of the hot reservoir, cold reservoir, respectively. Now, this slide is actually showing that same kind of model, but in regards to printed circuit board technology. So on the right, I'm showing a microsection or cross-sectional view of a microstrip circuit with a heat sink attached to it on the bottom. And a couple of things that we're going to assume for this thermal model. One is we're assuming that RF heating or insertion loss is going to cause some kind of heat rise. And we're also going to assume that the heat is generated at the signal plane and it has to flow through the dielectric to the ground plane to get to the heat sink. So the heat flow is through the dielectric itself. So the dielectric's acting as the thermal conductor. In the case of the ground plane, we're going to assume that the ground plane and the heat sink is at the same thermal potential. And in this case, I'm assuming that the ground plane of the circuit is attached to the heat sink by a TECA, as we call it, which is thermally and electrically conductive adhesive. I'll talk about that a little bit more later on. But anyway, with this in mind, there's several relationships that the designer should keep in mind. And to begin with, of course, increased heat flow is a good thing. Basically, you're trying to get the heat generated at the signal plane through the material to the ground plane and ultimately to the heat sink. So increased H is a good thing in the formula. And then thermal conductivity, obviously, if you increase that, you get a direct increase in heat flow. That's a good thing. If you use a thinner circuit, you have a shorter heat path, basically, and that also increases heat flow, so that could be advantageous. And then finally, a wider signal conductor would increase the area between the signal plane and the ground plane. That also increases heat flow. So another aspect now, besides the heat flow idea, is the insertion loss concerns. And for insertion loss, I've showed this these different charts before on some of the presentations. For you that have sat through some of these presentations, I apologize, but I think it's a really good way to visually understand the differences of circuits and how different components of insertion loss impact insertion loss. But there's 4 different components of insertion loss. There's dielectric losses, conductor losses, radiation losses, and leakage losses. I'm not going to talk about leakage losses today, mainly because our materials are so high in volume resistivity. Normally, leakage loss is not a concern. There are definitely exceptions to that, but for what we're going to be talking about today, that's not a concern. Radiation loss, that's another one I'm going to ignore today, and the reason why is because everything I'm showing today for data really has no concern with radiation loss, and radiation loss is plagued with a lot of variables. So there's a lot of design issues, some material issues, frequency, there's a bunch of different things. So thankfully, by the data I'm showing today, radiation loss is very minimal or not at all. So I'm really just going to focus more on conductor loss and dielectric loss. And the 3 charts that I'm showing below here, these are 3 different sets of circuits I tested using different thicknesses of 4350B, and I have it labeled as RO4835, which electrically is really the same thing. It's just as John Hendricks explained, the RO4835 has a slight different formulation to have much better long-term thermal aging, but electrically they do have the same performance. But essentially what I did was make 3 different sets of circuits using the same material, same copper, same everything. They're all 50-ohm microstrip transmission lines. And I'll start with the chart in the middle since it has the legend. And the thick purple curve is the measured data, going up to about 20 gigahertz, showing insertion loss on y-axis, frequency on x. And the other curves on there are actually some models from our MWI 2019 impedance calculator. And what it's showing is the green curve should match the measured insertion loss. That's the total loss that the model's predicting. And the nice thing about this model is it will tell you how much of that total loss was made up of dielectric loss and how much is made up of conductor loss. Conductor loss being the red curve, dielectric loss being the blue curve. And you can see in this case, in the middle chart, using a 10 mil thick substrate, there is more conductor loss, red curve, than dielectric loss, blue curve. Now, if you move to the chart to the left, using the same materials, maintaining 50 ohms and going thinner for the substrate, which means a more narrow conductor, now having more narrow conductor, you have less conductor to use, so you have more conductor losses, and the red curve shifts down. There are more conductor losses, basically, and insertion loss overall increases. And the increased insertion loss really has a lot to do with the increase of the conductor. So essentially, the thinner circuit is more sensitive to differences in the conductor. And then on the right side, chart on the right is same type of testing, except now it's a thicker circuit, maintaining 50 ohms. Now it's 30 mil thick substrate. And really what I'm showing there is the conductor losses are now no longer an issue. And it's really the dielectric losses that dominate. And that's a good statement, actually. For thicker materials, it's usually the dielectric losses that are dominant. Thinner materials, it's the conductor losses. So for power amplifiers at 6 gigahertz, they're generally thick substrates, so dielectric losses is pretty important. When you get to millimeter wave range of frequencies where things are thinner, then the thinner substrates, the conductor losses are pretty important. So that's kind of a way you want to separate these two different concepts for insertion loss. Now looking at some basic thermal management trade-offs considering the heat flow things I talked about and insertion loss, well, the ideal material would be to have a material that's very, very low in dissipation factor using smooth copper and a low dielectric constant, and also thin, and finally very high thermal conductivity. So that's ideal. Now, of course, as the designer is going through the process, they are juggling all kinds of different properties and what they want for material performance in their application, so they can't always use this ideal material. But just some more thoughts about some trade-offs. The next bullet down, basically what I'm saying is that the material can be used that actually has higher insertion loss, and actually is in many cases, but it's offset with having a much higher thermal conductivity. So a higher thermal conductivity, even though there's more heat being generated because of higher loss, having higher thermal conductivity actually kind of helps offset that. And then going the opposite direction, you can have materials very high in thermal conductivity, it could be very low in thermal conductivity. And then if you have that same material that's low in thermal conductivity and extremely low losses, low dissipation factor, very smooth copper, then that's another way you can kind of offset this thermal management issue. So for the materials being used in power amplifier for 5G, I've listed them below. And the 4835 material, again, that's the same material as 4350B from electrical performance, but the 4835 is a little better for long-term thermal aging and just being exposed to high temperatures for a longer period of time. You can see some of the properties there, and the dissipation factor is shown at two different frequencies. In general, it's considered a very low-loss material. The 4835 on the top row does have a little bit rougher copper, and you can see that in the copper surface rough numbers of 2.8 microns RMS. And then the thermal conductivity shown here of 0.69. Our general rule of thumb is anything greater than 0.5 watt per meter K is considered pretty dang good for thermal conductivity. So 0.69 or 0.7 is very good, actually. And then the next row down, the 4835 low pro, this is basically the same substrate as the 4835, except using smooth copper. And the smoother copper is obviously going to have less conductor losses. And so that's going to help reduce some of the insertion losses. And then also it's going to, of course, with less insertion loss, you can have less heat generated. And then having the very good thermal conductivity, whatever heat's generated, will be more effectively moved from the signal plane to the ground plane. And then TC350, that's been used a lot in the past for power amplifiers and most certainly being considered for sub-6 gigahertz 5G. And there you can see that that material is a little bit more optimum for thermal management, where you have lower dissipation factor and you're going to basically generate less heat. The copper surface roughness is okay. It's at 2.0. That's kind of rough, but considering this is usually a thick substrate for sub-6 gigahertz, the copper roughness is not quite that meaningful. But again, having a low loss, low dissipation factor, you're going to have less heat generated. And then you can see the thermal conductivity is quite high at 0.72 watt per meter K. So that's very good. So that's a good system to use when considering thermal management and just power amplifiers in general for the different properties that they consider. Now, just as of about a week ago or so, we released a new product called TC350 Plus. And what that is I would call it the optimized version of TC350. So TC350 works very good and has for years and years. It's just over time, just from learning more about how the material is used in different high power applications, we've optimized the material. And now the TC350 Plus, it has attributes that are actually more friendly to the circuit fabrication, longer drill life, things like that. And also it has a significantly improved thermal conductivity. So you can see that the dissipation factor is pretty close to the TC350, actually a little improved at 10 gigahertz. And the copper roughness about the same, but the thermal conductivity is probably one of the highest on the market right now at 1.24 watt per meter K. So that's a really good material to consider for power amplifiers at sub-6 gigahertz. So with that, I'd like to pass it back to John Hendricks and let him continue.
Okay, thank you, John Coonrod. Okay, so we're going to move on now to materials for antennas at sub-6 gigahertz. And previous generations of base stations, as I mentioned before, were often FDD and had strict PIM requirements, typically minus 163 dBc or better. And therefore very low loss PTFE materials were used, and there was a lot of stress placed on the smoothness and quality of the copper foil because that was one of the biggest drivers of having low passive intermodulation. It also somewhat restricted the use of thermoset materials, which tended to use slightly rougher copper. Because 5G systems use TDD and PIM is rarely an issue, that does allow the greater use of thermoset materials with a broader set of copper characteristics. I mentioned earlier, greater use of active antennas in 5G does drive the need for flame retardant materials, and there's a slide in a couple of minutes that illustrates the range of materials, some of which are flame retardants and some of which are not. The greater integration of 5G antenna structures, that actually includes a bunch of different things. So you tend to have now power dividers, you have what are called calibration networks, and of course you still have the radiating elements, which leads away from those bent metal designs and towards multi-layer PCBs. And that need for multi-layerable materials that continues to trend away, just on antennas now, away from PTFE materials and towards more thermoset materials. So that's kind of like the biggest difference you see with 5G. You see greater complexity in the antenna, multi-layer boards, and you see a need for thermoset materials and moving away from PTFE materials. Okay. So the next slide is a matrix of general materials of base station antennas. And the top two, again, those are the PTFE materials that were very commonly used and still are very popular in 4G antennas. That's the AD255C and the AD300D. That's dielectric constants of about 2.5 and 3. They are still the lowest loss materials. They are naturally flame retardant, but they tend to lend themselves mainly to double-sided applications where low PIM is required. For the thermoset materials, we have quite a large family there. The RO4500, that's 4533, 4534, and 4535. Those are typical RO4000 materials with dielectric constants in the range of mid 3.3 to 3.5. But only the 4535 is flame retardant, so only the 4535 lends itself to 5G antennas. The 4700 series materials were more interesting because in getting the dielectric constant down as low as 2.5 or 3, we added a bunch of what we call holospheres, which are glass hollow spheres that contain air and actually pull the dielectric constant down below what you would normally get with an RO4000 product. And there you see the 4700 JXR. Well, that was commonly used in a number of 4G applications, but it was also not a flame retardant material. The 4730 G3 is the flame retardant version of that, and that's the material that's become the most popular choice for 5G base station antennas at sub-6 gigahertz. There's just a minor reference at the bottom there to the relatively new material known as Kappa. That's actually, it's also a thermoset material, but with a dielectric constant of around about 4.4. That is typically a lower loss alternative to FR4, and comes into play typically for the radiators. It's normally a little high loss for the distribution networks, the power dividers, and the calibration networks, but it's proven to be quite interesting for the radiating elements where lower loss is not quite so important, but FR4 is not quite good enough. But we're not going to focus so much on that for the rest of the presentation. We're going to focus mostly on the 4000 materials for the power distribution networks and the calibration networks. So this slide sums up the RO4000 materials for antennas, but highlighted in green are the 4730 G3 and the 4535. So the main differences in terms of performance, you see that the first row is dielectric constant, and you see the 4730 G3 has a dielectric constant of 3, and the 4535 has a dielectric constant of something close to 3.5. And then going down a couple of rows, you see the loss tangent or the dissipation factor, where the 4730 G3 is 0023, and the 4535 is 0032. So again, if you want the lowest insertion loss and the lowest dielectric constant, the 4730 G3 is the best material. It does contain those holospheres that pull the decay down, and that does add somewhat to the cost of the product. So 4535 is a lower cost product than 4730 G3. In either case between those two materials, you have the option of the smooth reverse treat low pro copper or the standard rougher ED copper. Now, the low pro smooth copper was originally developed for an antenna material to reduce passive intermodulation, but it does have other advantages. It does actually have an effect. A rougher copper will increase the visible effective dielectric constant of the circuit because it increases the path length. And if you have a rougher copper, then you also have greater variation in copper roughness, which then leads to a greater variation in effective dielectric constant. So the advantage of the low pro copper, whether you're talking about 4730 G3 or 4535, is essentially a tighter control of dielectric constant. So with either case, the low pro gives you tighter control of dielectric constant. So then you're kind of left with a choice, the 4730 G3 with low pro, the 4730 G3 with ED copper, and then the 4535 with low pro, and the 4535 with ED copper. And essentially, the 4730 G3 is lower loss, it is lower dielectric constant, but in either case, with the low pro copper, you get a tighter control of dielectric constant with the smoother copper. And that's essentially the portfolio that is being promoted for 5G sub-6 gigs antennas right now. And just as you see at the bottom of that slide, from top to bottom, the G3 with low pro, the G3 with ED, the 4535 with low pro, and then with ED copper, that's kind of from top to bottom, the best performance to slightly less good performance, and it's also valid for price as well. So the 4730 G3 would be the most expensive of those products, and the 4535 with ED would be the most cost competitive. And so essentially you pay your money and you take your choice, and that's largely what designers are going for now with 5G antennas. And with that, I'm going to hand back to Mr. Coonrod.
Well, thank you, sir. And I'm going to continue on talking about the materials for antennas at sub-6 gigahertz. And as John explained previously, the 5G technology and the protocol they're using is really time division duplex, though they have much less issues with PIM. I would not be surprised if there's some niche things out there that are still going to have issues with PIM. And the reason I bring that up is because most of our antenna grade materials are formulated to have very low PIM. But from what we see so far, though, most of 5G applications, that's not an issue. The materials of choice right now for 5G antenna applications are listed here in green, 4730G3 being the dominant material. The 4835 and the RO4835 Low Pro also being used, and then finally the RO4535, as John mentioned, a little bit lower cost. The nice thing about all of these RO4000 materials is they are very friendly to the PCB fabrication process, so making the yields and the costs of actually building the circuit a little bit easier. This table information is just giving you a quick overview of these different materials. And one thing I wanted to point out is the RO4730G3, again, the dominant material used in this application for 5G. It does have a thermal conductivity in the range that I'd consider moderate, not necessarily good. But the reason it's being used, though, is because it is lower loss for dissipation factor and a smoother copper, so it's going to generate less heat. So thermal conductivity is not quite as important. Also, for antennas, thermal conductivity is usually less of an issue, but there are situations when you're looking at power dividers associated with antennas, feed networks, things like that. So thermal management most certainly can be an issue with antennas. But again, 4730G3 is really the material that's used most often in these applications and does quite well for thermal management. Due to timing, I'm going to move on to another topic that I want to talk about that has to do with plated through-hole vias. I'll quickly talk about insertion loss here, where I'm comparing the RO4730G3 to the RO4835 Low Pro. And the G3 does have, the RO4730G3 materials does have a little bit lower insertion loss because it's using a material or substrate that does have a little lower dissipation factor. In this case, they're both using the same copper pretty much for copper surface roughness. So the difference here really comes down to a dielectric loss difference. Now, what I really want to get to here that is, I think, pretty important is the RO4730G3, as John Hendricks mentioned, is using a rather unusual filler. It's a hollow sphere filler. And just by the nature of that material, when it's drilled in circuit fabrication, the plated through-hole via that you will get and see in a microsection, the through-hole wall of that via is going to be rougher than what a other type of material would be that doesn't have these hollow sphere fillers. And because of that, the circuit fabricators that look at microsections day in and day out, they saw that and they thought that was unusual. So they raised the flag some time ago. We had our technical service engineers get involved, and they've ran many, many studies, and we have a lot of detail if anyone's interested. But we looked at different things for circuit fabrication, processing, and also plated through-hole reliability, looked at multiple lead-free soldering, sequential lamination, a bunch of things. And even though the plated through-hole via roughness of the through-hole wall does look unusual, and it really does, but that's the nature of the beast, it really does not cause an issue for printed circuit board fabrication or long-term reliability. And I've given a picture there to the bottom right that's showing a plated through-hole using the RO4730G3 materials. And you can see that the through-hole wall is pretty rough, actually, compared to what you would normally see. Now, along with that study, we decided to take a look at RF performance or potential of RF performance due to the plated through-hole wall being rough. Because as we know, the roughness of the copper most certainly can impact insertion loss and phase response in a planar sense. So the copper roughness, as we make the laminate, the substrate copper interface, that roughness we know, and we have many papers on this topic, we know that that does impact insertion loss and phase response. But we weren't too sure about the copper roughness of a plated through hole. So what we decided to do is do a study on this, and I used two different materials. One, the 20.7 mil thick RO4730G3 laminate, which again is the dominant material used in 5G sub-6 gigahertz, and the other is a 20 mil RO3003G2 laminate, which is actually an unusual material because we normally don't offer that thickness, and that material is actually optimized for millimeter wave applications, 60 gigahertz, and actually more dominantly 77 gigahertz. But anyway, I used that material in contrast of the 47G3 for its potential to see differences in plated through-hole wall. So for the RO4730G3 material, the hollow spheres is going to cause a plated through-hole wall. It's pretty rough. The circuits made on the 20 mil thick RO3003G2, being that it does not have hollow sphere filler, does not have glass weave, and the filler is extremely small and spherical and not hollow, those plated through-hole vias have through-hole walls that are very smooth. Now, assuming that the printed circuit board fabrication process is well controlled, and we did work with our fabricator to make sure it was very well controlled, but assuming that, then the plated through-hole roughness for circuits made on RO4730G3 should have a pretty rough through-hole wall as compared to circuits made on the RO3003G2 materials. So this is our test vehicle on the right side. It behaves like a microstrip circuit, kind of, sort of. It really is a loosely coupled grounded coplanar waveguide, and electrically it does behave like a microstrip circuit. And what we're doing here is the top and bottom view I'm showing, I have in-launch connectors. So basically on the top copper layer, I have an in-launch connector on the left side, and the bottom copper layer, I would have a connector on the right side. So going from left to right, I have the connector on the left in the top layer. Signal goes off to the middle of the circuit. I have a via that vias down through the circuit from copper layer 1 to copper layer 2. And then the RF path continues to the right to the connector to the right. So we're basically going through a via that transitions in the middle of the circuit, the signal trace. And that via is the via that we're going to microsection and look at in great detail. And I looked at a lot of different measurements for this type of test vehicle where we measured unwrapped phase, which turned out to be the most accurate. But I also did measurements with impedance, insertion loss, group delay, a variety of things. And if more information is needed on this topic, in December edition of Microwave Journal, we did show great details in an article in that magazine. So you can get a lot more information in the December issue. So moving on. This is an output of just trying to show you what kind of information we collected. This is really an output of some of the circuits that we tested for the 20 mil thick RO3003G2. And essentially what we did is we started off with a large panel, cut it in half, and one half panels had circuits made, and the other half panel also had circuits made, but in different times because we were trying to see differences in panel-to-panel variation due to circuit fabrication. So we know that etching and copper plating thickness can impact that via in the middle of the circuit and the coupling around that is there for impedance matching. So we know that does impact phase response and other things, so we kind of wanted to see what differences we could see from panel to panel. So that's why we had two panels of the same material and then looked at the circuits for panel-to-panel variation. And then we took unwrapped phase measurements. And in the table information shown below here, the orange header columns at different frequencies is showing the unwrapped phase measurement angles, and at 24, 28, and 39 gigahertz. And then the information under the yellow header, that's basically setting circuit P1C1, P1 panel 1, C1 circuit 1, as the reference, and then comparing the other circuits on that panel, P1, to the reference circuit and showing the differences of phase angle to the P1C1 circuit. And then the statistics off to the right are for just panel 1, and then on the bottom right is the statistics just for panel 2. Now, all things considered, and roughness of the plated through-hole wall, and also the different etching and copper plating thickness and other variables for circuit fabrication, having 4 or 5 or 10 degrees difference in phase angle at 39 gigahertz, let's say, is actually a pretty small number. But continuing on here, looking at some of the pictures of the microsections of the circuits that we tested, the blown-up version of a circuit based on RO3003G2 material shown to the right, and you can see that the copper-plated through-hole wall is actually very smooth, as it should be. And then the middle picture that's kind of blown up, that's circuits that are made on RO4730G3 materials, and you can see that the copper plating is pretty rough in the plated through-hole wall, and that's kind of what we expect too, nature of the beast, kind of. And then continuing on, this is really a quick summary, and there's a lot more information in this study, but this is a quick summary of what came out of this study. And so we had 2 different panels, 6 circuits on each panel for each material, so a total of 12 circuits for each material. We looked at the unwrapped phase measurements, and really what I'm showing below is just an output of the differences and the statistics of the differences of the circuits on each panel. We did a quick repeatability study, and we found that our test method, using the exact same test vehicle, using different calibrations, using different things, has a repeatability about plus or minus 1.2 degrees at 39 gigahertz. So when looking at the standard deviation numbers below here, you might want to keep that in mind. Also, if you look at the range numbers, then obviously double that is about 2.4 degrees just for test method repeatability. So if you look through all the numbers here, and I have a lot, you do see differences, of course, and that's normal. But in the grand scheme of things, there really is no significant difference due to the plated through hole roughness being smooth for the data on the left and then being a rough through hole wall for data on the right. And that's a quick overview of the plated through hole roughness concern, and I'd like to pass it back to Mr. John Hendricks.
Okay, thank you, Mr. Coonrod. Okay, we'll push on to the last section here. This is just a brief introduction and summary of the differences with 5G millimeter wave. So you have the high frequency band, as I mentioned before, and the applications of fixed wireless access. What are the differences? Well, typically now the printed circuit boards are high count multi-layer boards. They can be 20 plus copper layers, and typically you need a range of thinner materials that Rogers hasn't always had before. The materials need to be HDI, high density interconnect compatible, which means sequential foil lamination compatible, and a smooth copper with a good foil bond. And to achieve this, we've launched a new family called RO4000T, or the thin RO4000 family has been launched. We do have some PTFE alternatives for the lowest loss and the lowest dielectric constant, but the 4000 family is the one that's generating the most interest. So the next chart is just a quick matrix. We do have a thin RO4730 G3 material for millimeter wave antennas. Typically that would be the top layer on your multi-layer board, possibly. Then you have those two alternative families. You have the CLTE MW, which is the low loss, low dielectric constant PTFE material for the tightest applications, and we are developing a matching bond ply to go with that. But perhaps the most interesting one now is the RO4835T, which is a laminate, the RO4450T, which is a bond ply, and the CU4000 and CU4000 low pro copper, which we supply in order to enable foil lamination. So you can do 2, 3, 4 stage sequential foil laminations to achieve HDI requirements that you have for millimeter wave applications. And I'll just briefly expand on that a bit. So whereas before we only had RO4000 in quite thick blocks, 4 mil, 10 mil, for example, now you have the 4835T laminate, which goes down as low as 2.5 mil, 3 mil, and 4 mil. It has the advantage of spread glass reinforcement, so you have a much more consistent and evenly spread homogeneous material when it comes to dielectric constant. The 4450T, also 3, 4, and 5 mils, so a greater variety of thicknesses there, and those bond plies are fully compatible with foil lamination to enable you to achieve HDI. And we're still working on it. We're still expanding it. We're working on more thickness variations, more bond ply variations. So the whole family of RO4000 is expanding in terms of thickness offerings in order to better enable high count multi-layer boards at millimeter wave frequency ranges. Don.
Okay, I wanted to talk a little bit more about some of the technical details of the materials used at millimeter wave. And this table of information gives you a quick overview of that. The RO4450T prepreg, that a lot of time is used in combination with the RO4835T core, where the core is used on inner layers and the RO4450T prepregs on the outer layers. And I'm showing the copper roughness values here of these materials, and they are correct. They are depends on what copper you use for the foil lam, obviously. The CU4000 low-pro copper foil that we supply is optimum to be used with this prepreg, the RO4450T. And you can see also the thermal conductivity for both these materials are in the range of considered very good, actually. So that's one thing to consider. Then the 4835 low pro that's just below there, that's a material that's often considered in millimeter wave 5G applications. Again, you can see it's pretty smooth copper, which is very important for millimeter wave where you're using thinner laminates. And also it's got a little bit higher thermal conductivity as well. And then the 4730G3, we've talked about that already some. And then the last two materials I'd talk about quickly is the RO3003 materials and the CLTEMW. These are both PTFE-based materials. So for circuit fabrication, they're a little more challenging than the 4000. However, they are used in very high volume right now, so that's not a problem. It's just a little different for circuit fabrication. But one thing worth noting is the dissipation factor are very low, extremely low for these materials, so you will generate less dissipation factor, less dielectric losses and overall less heat generated. So looking at the charts quickly, these are insertion loss charts going out to 40 gigahertz. The lowest loss curve here is the 5.7 RO4730G3, and then followed up with the 5.7 RO4450T prepreg. After that is the RO3003 and the CLTEMW materials 5 mil thick. That's using ED copper. If those materials were clad with rolled copper, then the insertion loss curves would look a lot different, which they can be. They are capable of using rolled copper. And in that case, at 40 gigahertz, you'd be up around about 0.62 and 0.68 for dB per inch losses of the RO3003 5 mil and also the 5 mil CLTEMW respectively. And then the last thing I wanted to comment on is the green curve, which is the 4 mil thick RO4835 low pro, which has the most insertion loss on here. But considering 1.5 dB per inch at 40 gigahertz, that's actually very low loss. So on this chart, it is the lossiest material, but that's still considered very low loss. Another thing I'd like to give out here is really some reference information. I don't have time to go through this in detail, but this combined with information on the previous slides have on copper surface roughness numbers, and the information combined here should allow the RF designer to have all the information they need to do RF simulations using electromagnetic modeling software. And one thing I want to point out here is on the previous slides when we talked about design decay, that was the bulk design decay or the intrinsic design decay of the material. And that value is actually proper to use when using electromagnetic modeling software that does account for the copper surface roughness in regards to phase response. However, some of the electromagnetic modeling software does not account for copper surface roughness in regards to phase response. In that case, you should be using the design decay shown here that is frequency dependent. So that's why I'm showing these numbers. And then below there is prepreg. And prepreg is a little different because prepreg can be used many different ways. And if there are no copper effects, in the case of a prepreg that's between two etched laminates, there are no copper effects on the prepreg, then the design decay is as shown on this table of information. However, if there's copper effect on one side, like a foil lam, and the other side is a blank core with no copper, then that's a different effect because we know that copper roughness does impact the phase response and the perceived dielectric constant of the circuit we call design decay. And then also if you have two copper surface effects on both sides of prepreg, that's a little different too. So that's the paragraph of information that I've shown below here. So that's really the presentation for today, and I'd like to thank Mr. John Hendricks, and also I wanted to give you a quick overview of our Rogers Technology Support Hub. This is something we're really proud of. We have a lot of good information here and would like to invite you to become a member. So on here you can find different calculators, impedance, loss calculators, CTE, coefficient thermal expansion calculators. So we've got a lot of different things that are all free on here. And then also we have Raj mobile apps. We have a variety of technical papers, sometimes given at different conventions, sometimes short papers or blogs, but a lot of different information. We have a pretty large video library at this point. And then also we have a section to where you can contact an engineer local in your area. So with that, we may have a few minutes for questions, but I think we may have cut it a little tight.
John and John, thank you very much, both of you, for a very informative presentation. I've found with Rogers webinars, there's always a ton of information, a lot of good detail, and I'm sure our viewers appreciate that. We're almost out of time, but let's, since we do have a few questions in the queue, let's see if we can't go through a few of them, and then John and John will get all the questions, so those that we can't answer today, they will have for possible follow-up. So the first question, in thermal management, what is the range of operating temperature for cooling a device in 5G?
I guess I'll take that, but unfortunately I don't have a good answer unless John Hendricks does. The bottom line is what I keep preaching basically, as long as the circuit does not violate the MOT of the circuit board itself, and that's really the temperature you want to avoid. There are devices on the circuit board that need to be considered as well. So I don't actually have a magic temperature or temperature range. As a default, though, usually 105 degrees C or less is good for printed circuit board technology based on our materials. And there are some devices that cannot tolerate that, some as low as 75 or 80 degrees C. But those are just general numbers, unless Mr. Hendricks has a better way to answer that.
I don't. I mean, we're cautious before saying what people can and cannot do, but typically that kind of 100, 105 is a reasonable rule of thumb. Some people operate higher, but obviously the goal of having higher thermal conductivity materials is that you don't actually reach those higher temperatures and stay well below the MOT, which is always advisable.
All right, a second question. How well does the smoother copper adhere to the substrate in the Rogers 4835 Low Pro compared to the rougher copper of the Rogers 4835?
John, you know, you go, John.
Yeah, I was just going to say quickly that the 4835 Low Pro does have a very thin layer of, I guess I'd call it a bond enhancement between the copper and the substrate. And because of that, the 4835 Low Pro may have just a slight higher peel strength than the standard 4835 with the rough copper. So the bulk substrate is the same, but there is a very thin layer between the copper and the substrate in the case of the Low Pro, and that does actually help the peel strength be as good as the standard 4835 or slightly better even.
Yeah, I think it's typically slightly better, but I would add that the best thing about RO4000 when it comes to copper bond is that unlike almost any other material, that copper bond stays where it is through multiple thermal cycles. Almost every other material that you will see when going through multiple thermal cycles will see a degradation in copper bond. RO4000 doesn't, and that's just about the most important thing. It stays where it is at the beginning, right through thermal cycling.
Okay, one more question. We have a viewer who's working in KU band and KA band and wants to get some guidance on which frequencies should he or she be worried about the conductor loss?
Good question. And the general rule of thumb is if you look at skin depth, that will tell you at what frequency the copper surface roughness becomes more important. And I think of copper roughness and frequency and skin loss all kind of related together, and it is related to conductor loss. So basically what I'm saying is at lower frequencies where the skin depth is very thick and the copper surface roughness is really not coming into play, then the conductor losses are not augmented by the roughness. But once you get to high enough frequency where the skin depth is thinner than the copper surface roughness, then the roughness will impact the conductor loss a lot. Now, if that roughness of the copper happens to be very smooth, like Low Pro, then it's not going to make much difference. If it's rougher, then it is going to make more of a difference. So there's a lot of it depends in this answer, unfortunately. But that is true. And as just a general statement, I can see differences in conductor loss of rough copper versus smooth copper as low as about 6 to 8 gigahertz, actually, depending on materials. But it can happen at lower frequencies than what you might think. Again, it has a lot to do with skin depth and the roughness of the copper, though.
All right. I think this next one should be a quick question. Do you provide photoresist boards for Rogers 4535 and Rogers 4730 G3?
No, we don't do that, and there's a few reasons, and I'll just be quick about it. But basically, it's because photoresist does have some kind of shelf life, and also it's photosensitive and all these different things, and it can behave different with different types of copper. And there's just a lot of variables that we just can't, control as well as we'd like. So we do not provide that.
All right, and then the last question I'll ask you: how about the effect of electromagnetic radiation in the 5G scenario with respect to design parameters for sub-6 gigahertz?
I guess I'll try that one too, unless John wants to jump in. But my perspective is usually radiation losses, they are frequency dependent. So radiation and radiation losses are frequency dependent, and basically the higher frequency you go, the more problematic they are. At sub-6 gigahertz, usually radiation is less of an issue. And I say usually because it is very much design dependent. So if you have very abrupt impedance anomalies, like a stepped impedance structure or something like that, where you go high impedance, low impedance, at those very abrupt impedance transitions, you can get radiation even at the lower frequencies. So typically, I worry about radiation when I get up around 20 gigahertz or more, but usually sub-6 gigahertz is less of an issue. But there are, like I said, there are some design issues, and there's some other things that can come into play.
Okay, well, unfortunately, we've run out of time. We're past the hour, and we have a few more questions left, but John and John will get copies of those, so any key ones they can provide follow-up. I'd like to thank John Hendricks and John Coonrod, both of Rogers Corporation, for the presentation today on high-frequency materials for 5G base stations. Very informative. Reminder that the webinar has been recorded. It will be available to watch again within about an hour from now. You can find it at the events section of the Microwave Journal website. From our homepage, click on Events, then Webinars, and you'll see a link to the archives at the top of the page, and that's where you will find this recorded webinar. So if your colleagues would benefit from watching the presentation today, please do let them know. Thanks, everyone, for joining us.